Today we shall continue with where we stopped yesterday. We start introducing some models that may be useful for modeling physical processes. And today we'll go more in detail with these models. And in particular, what we shall discuss today are these topics. First of all, we will introduce models for physical processes. I recall you that we will discuss in the next days about physical processes, but is today, chemical processes, but will be tomorrow, and biological processes, that will be next week, and that will be the conclusive part of the class. Concerning physical processes, we shall discuss today how we may model absorption processes, but is, as you may know, fundamental process when you have to deal with ecotoxicological issues. And then we will introduce balance, transport, and chemical reaction models. Today we will end up with chemical reaction. We will take over tomorrow and finish chemical reaction models tomorrow. So, what are ecotoxicological processes? We have seen yesterday that we may subdivide the biosphere. We may subdivide the environment, the space that is around the surface of our planet into four interconnected spheres: lithosphere, hydrosphere, atmosphere, and biosphere. So ecotoxicology deals with introducing models of ecotoxicological processes in order to describe how toxic substances are found in several forms in the different spheres, and how, in particular, these substances can move from one media to another. By now, we interpret the term media by referring to the lithosphere, hydrosphere, atmosphere, and biosphere. We have seen yesterday that spheres can be in equilibrium with each other, or maybe in a condition of dynamic exchange phenomena, but somehow may also maintain a kind of steady state or equilibrium condition. We have seen yesterday's various types of equilibrium, but maybe relevant when describing ecosystems, or while trying to implement mathematical modeling on ecosystems. Now let's focus on ecotoxicological processes. Let's start with some definition, but I assume you already know, because you should have already seen this definition in our classes. First of all, we shall introduce the concept of bioaccumulation, that refers to air, water, soil, and food. Bioaccumulation, in general, may be subdivided into two sub-processes: the process of bioconcentration and the process of biomagnification. Bioconcentration typically happens when we have a particular substance. Let's imagine a toxic substance that is dissolved in water, and then due to exchanges, we have seen that water is a key solvent that moves all the elements through, in and out the ecospheres. So bioconcentration refers to the fact that when we have a dissolved substance in water, due to biological processes, we may have a concentration or an increase of concentration of this substance from the water into some of the other spheres. So from the hydrospheres into the lithosphere or biosphere, or the atmosphere, and so on. So bioconcentration has to deal with substances that are concentrated from dissolved quotas in water. We have an important concept, but it resides into the concept of bioaccumulation, is the concept of biomagnification. Biomagnification refers to substances that are delivered through food webs. Food webs are networks of exchanges of resources in living systems. So through food webs, we may have toxic substances that are displaced toward the four spheres, and in this case, due to the characteristics of several biological processes, we may have an effect of biomagnification of the concentration. In particular, biomagnification refers to the fact that substances that are found in the other spheres, lithosphere, hydrosphere, or sometimes atmosphere, may be found in increasing concentration into the biosphere. So living systems have the ability of concentrating substances coming from the other system. We said that when we discuss, we implement ecotoxicological models, we seek for a kind of equilibrium conditions. In particular, if, for example, we concentrate on the exchanges between the lithosphere and hydrosphere, so the equilibrium of exchanges of substances that are found in the lithosphere or that are found in the hydrosphere better and that are transferred to the lithosphere, we talk of a process that is well known and is known as with the name adsorption. Adsorption is the movement of a dissolved substance from the water column toward the solid, toward the suspended solid quota. So this is really movement of something from the hydrosphere to the lithosphere. The adsorption process is normally is modeled by isotherms transformations. So this means that temperature is assumed to be constant during the process of reaching of equilibrium, the process of equilibrium reaching. And the four very general model we may employ for describing the adsorption process are the Redlich-Peterson, Freundlich isotherm, Langmuir isotherm, and finally the partition coefficient, that is the most general approach. Now let's go into some details in describing these models. First of all, we shall observe that contaminants and pollutants, like for example pesticides, heavy metals, but also nutrients, but as we have seen may be considered somehow pollutants, are found mainly in the sediments of aquatic ecosystem or in the suspended matter. What does this mean? This means that in general, if we have some dissolved into a water column, we may expect that these dissolved substances shall be transferred from the hydrosphere to the lithosphere, and the process that describes this transfer is called adsorption. The equilibrium, that is a dynamic equilibrium, is normally achieved very quickly. So after a short initial transient in which we have a significant gradient in concentrations between the two spheres, then quite quickly a steady state condition is reached in which we have an exchange, a phenomenon of exchange from the hydrosphere to the lithosphere, and symmetrically contemporary the reverse phenomenon of exchange from the from the lithosphere to the hydrosphere. So we are talking about adsorption going from the hydrosphere to the lithosphere, and desorption going from the lithosphere to the hydrosphere. And we can, in general, model this kind of processes by employing kind of isotherms models, but depend essentially on the substances involved. The substances involved, in particular in the adsorption processes, are the adsorbent, so the surface of the suspended solid on which the toxic substance is attached on, and the adsorbate, so the toxic substance itself. Essentially, this is a surface process, so the solid surface of the sediments are mainly involved, and the very general model that we may conceive for describing this process says that if Qs is the adsorbed fraction, so the concentration in the solid of the substance we are focusing on, and if Cs is the water concentration of the substance, the absorption process in isothermal condition may be described by such kind of model or equation, in which we have an equilibrium constant K multiplied by the concentration in water divided by a dimensionless generalization constant delta plus a constant H that is related to the heat of absorption. This is called H exactly because it refers to the thermodynamic function enthalpy, multiplied by the concentration in water elevated to an exponent beta. That is again a dimensionless heterogeneity factor. This is a very general model by which we can describe many real situations of exchanges between the hydrosphere and the lithosphere, so of absorption processes. In particular, from this very general equation, we may find some specific application. For example, if we put the generalization constant delta equal to 1, then we resort to this very simplified model. So the concentration in the solid is equal to a constant K multiplied to the concentration in the liquid divided by 1 plus H, that is the enthalpy or the energy of, the energy related to heat of absorption, so to heat that is released during the phase of absorption, multiplied to the concentration in water, Cs, elevated to the generalization factor, the multi-layer called dimensional heterogeneity factor, describing if the absorption is single, multiple, or multi-layer. And in this case, so the model is reduced like that. Another simplification is given by Langmuir isotherm, but it assumes an homogeneous adsorbent surface. So here we do not take care about the heterogeneity factor, but is the constant beta is placed equal to 1, and a monolayer absorption with capacity K over H. You can see again the model is quite simplified. We have delta equal beta equal 1. So the concentration in the solid phase is then expressed as K, that is an equilibrium constant for the process, times the concentration in the liquid divided 1 plus the heat of absorption times the concentration in the liquid phase. We shall notice that the process of absorption depends dramatically on the characteristics of the two elements involved. So the adsorbent and the adsorbate. I recall you that the adsorbent, in my view, in our view here, is the suspended solid, on which the adsorbate, that is the toxic substance, may be sticked on by the adsorption processes. From this simplification, we end up by a simple algebraic manipulation with this model. Concentration in the solid is equal to K times concentration in the liquid. If we divide by Cs, then we have that the ratio between the concentration in the liquid and the concentration in the solid is equal to H divided by K times the concentration in the liquid plus 1 over K. If we make some experimental observations, for example, if we measure in a real environment the concentration in water and the concentration of the substance on the suspended solid, depending on the characteristic of the adsorbent, so if the suspended solid is loamy, sand, loam, clay, loam, or clay, you will have different behaviors. So you will have a different fraction of the concentration in the liquid, C, that will be found on the solid. So as these lines grows, this means that the concentration in the solid is decreasing as the concentration in the liquid is increasing. So to a greater concentration in the liquid on a growing, so to a greater concentration in the liquid, you will have a smaller concentration in the solid. Of course, these plots that come from experimental observation describe the fact that different adsorbent substances, clay, loam, sand, and so on, have different capacity of hosting substances from the water column, from the dissolved quota to a solid quota. Finally, we shall concentrate on the Freundlich isotherm, which we have the Freundlich isotherm, as I have already introduced, is the second, Langmuir, Peterson, and yes, the Freundlich. For the Freundlich isotherm, we assume that the heterogeneity factor is 0, so we simplify the general model by putting delta equal to 0. And the Freundlich isotherms assumes an heterogeneous adsorbent with adsorption sites that are all energetically non-equivalent. So this means that there are different adsorbent sites or absorption sites that have different heat of absorption. So whose energy released in the process of absorption is different. With this simplification, the model, the general model we have introduced, becomes that the concentration in the solid phase is simply proportional to a constant A to an exponent to a power of the concentration in the solid phase. So concentration in solid is proportional through A to the concentration in the liquid phase elevated to a power gamma. Gamma, of course, is equal to 1 minus beta. It is immediately obtained from algebraic consideration from the general model. And the constant A that is equal to K over H, so the equilibrium constant of the absorption process divided by the heat of absorption, is called the layer capacity. So the capacity of a layer to absorb the sorbate. If we plot these graphs with three isotherms of absorption, I recall you that we are in isothermal condition. This means that the temperature is assumed to be constant. And here we are simply plotting what happens to the concentration in the liquid phase, what happened to the concentration in the solid phase as the concentration in the liquid phase changes. So we have three different curves describing this process. The Redlich-Peterson, the most general one. It is a continuously increasing curve that describes that the fact that as the concentration in the liquid increases, when you have a continuously increasing concentration in the solid, then we have the Freundlich isotherm, that is constantly growing, but not so much growing. So much more a plateau, reaching growth, but always growing. And then we end up with the third model, that is the Langmuir model, in which we have a plateau, which the process of absorption is in a perfect dynamic steady state. So this means that in the case of a Langmuir isotherm, when we are in steady state, we have the quantity of material that is absorbed that is equivalent to the quantity of material that is desorbed. So what we are describing here, we are describing the movement of substances from the dissolved quota in the water column onto the suspended solid, but pertains to a lithosphere, as we said. The last model that is in general, the more general model, if you want, but may apply for describing the process of absorption, is called the partition coefficient model, in which we simply write that the concentration in the solid phase is equal to the concentration in the liquid times a partition coefficient K. Here we are simplifying at maximum our description, meaning that we are employing only one parameter for describing the huge or complexity of all the processes that come into play in the case of processes. In this case, we may say that K, the partition coefficient from experimental observation, may be made equal to a fraction of organic carbon, so it is the percentage of organic carbon that is present into the absorbent. So this is the fraction of the organic carbon is a characteristic of the adsorbent. So total carbon fraction in the solid matter times the KOC. KOC is the organic carbon partition coefficient that describes how organic carbon partitions from solid to water. So this organic carbon partition coefficient that is expressed in milligram per gram of carbon, so milligram of the substance, the toxic substance we are studying per gram of carbon content in the adsorbent divided by milligram per cubic meter. So this is a partition coefficient that describes how matter in the solid part or our substances partitions from the solid quota onto the dissolved milligram per cubic meter quota. So from experimental observation, we realized that we may write the absorption model simply by hindering all the complication into the partition coefficient K, and we can further express the partition coefficient K as the product of two constants, one the fraction of organic carbon that describes the quantity of organic carbon into the adsorbate, and KOC, that is a characteristic of organic carbon in terms of partitioning. So this is as to say that we look at the adsorption process as if the toxic substances sticks onto organic carbon, and in proportion, as a proportion of the content of organic carbon of the adsorbent, and time the partition coefficient for water and solid of organic carbon. So we move the substance from the water, from the hydrosphere onto the lithosphere by employing these two parameters. Again, remember that these are parameters of your model, so the more parameters you have, the more will be your calibration effort. We have some indication again from experimental observation that KOC, so the partition coefficient for organic carbon, is directly proportional to KOV. KOV is the partition coefficient octanol water, and the proportion is obtained through this simple relationship. We can find this kind of values from literature or empirical relationships or observation, but we can generalize this law by simply, for example, writing that the KOC is equal to a constant alpha times the KOV elevated to parameter beta. So if we pass to the log of this relationship, we obtain that the log of KOC is equal to log alpha plus beta log KOV. So there is a linear relationship between log KOC and log KOV. What is KOV? KOV is a characteristic of a contaminant or of a toxic substance that we are looking at. Remember, FOC and KOC are characteristic of the adsorbent, while KOV is a characteristic of the adsorbate. In reality, KOC is includes also characteristic, includes the relationships between the characteristic of the adsorbent and the characteristic of the adsorbate. What is KOV? The octanol water partition coefficient KOV is a coefficient representing the ratio of the solubility of a compound in octanol, that is a non-polar solvent, to its solubility in water, that is the most general polar solvent. You may remember, we introduce water. Water is a very sharp dipole with a very net difference, with a very net displacement between negative and positive charges. This is water. You remember my picture of Mickey Mouse, the large atom of oxygen that is generally negative, charged negative, and the two small atoms of hydrogen that are in water, that are in general positively charged. KOV tells us that the higher to KOV, the more non-polar the compound is. The higher the KOV, the more the non-polar means the more the substance, the toxic substance, tends to stick to non-polar substances, so away from water, typically lipid. Log KOV is generally used as a relative indicator of a tendency of an organic compound to absorb to soil. Log KOV values are generally inversely related to aqueous solubility and directly proportional to the molecular weight. These are all observations that come from experimental measures. For example, environmental engineers like to employ these abacus graphics. Here we have plotted the ratio between concentration absorbed into a solid phase, QS, divided by the concentration in the liquid phase. So that is the fraction of absorbed material. And we are looking how this ratio, this fraction, changes as a function of KOV. Typically, we can say that for weak sorbers, so for those substances that do not have or do have a very high energy absorption, so for those substances that needs high energy in order to be present a useful sorption surface, so weak sorbers, we have low values of this ratio. This means that you will find, for weak sorber, you will find the substance mainly in water, in the liquid fraction. On the contrary, for strong sorbers, what are sorbers but are very prone substances or adsorbent sorbers that are very prone to get to host toxic substances from the solid quality in the water column. So for strong sorbers, you have the largest values of the fraction. This in particular, here we have 1. This means that for strong sorber, you will have that the concentration in the solid phase is exactly equal to the concentration in the liquid phase. Of course, these relationships are non-linear. Instead, they represent a kind of sigmoidal behavior, this kind of S-shaped curve. We have different curves depending on the suspended solid concentration. So at higher suspended solid concentration, you will have faster absorption processes, and a lower suspended solid concentration, you will have slower absorption processes. And then you will have, from these graphs, you can see that, for example, if you look at the various substances, these are classification classes of different substances. For example, pesticides. These are box and whiskers representation of KOV, better log KOV values for several pesticides. I recall you that the box and whiskers gives you an idea of this. The first line is the median, this one is the maximum, this one is the minimum value. But for example, for phenols, we will have a lower value of a log KOV, meaning that phenols are in general tending to be dissolved, while, for example, pesticides generally tends to be absorbed onto particulates. So this kind of abacus for engineers are very useful because they give you a first hint or a first suggestion on where you may expect to find the toxic substances, depending on the characteristics of the substance itself, so the KOV, and depending on the characteristic of the sorber, weak or strong sorber, and depending on the concentration of suspended solid, so how much material available for adsorption process is there. So you see these kind of considerations, this kind of graphs, try to include to a single drawing all the variability or complexity or heterogeneity of a process, of the various aspects that govern the adsorption process. If this has to do with exchanges between hydrosphere and lithosphere. So here we are discussing how substances are transferred from the liquid phase onto a solid phase. So you have a log KOV graphs through the partition coefficient model. That is the very general application, general model you may apply to describe this. If we are more focused on toxic effect on living organism, we may focus our attention on the equilibrium between hydrosphere and biosphere. First of all, we try to understand how much of, or how much and how the substance, toxic substance, particular molecule that is dissolved in the water column may be found into the body of living organism. Now, but we have introduced our subdivisions into the geospheres, we know that this process has to do with equilibrium between the hydrosphere and the biosphere. How do we model this kind of transfers? We employ a bioconcentration factor model. So we write what a bioconcentration factor that is equal to the concentration in the biota divided by the concentration in water. The concentration of the lipophilic organic compound in the fat tissues may be written as the concentration in the biota divided by the fraction of lipids that are presented in the biota. So this kind of transfer depends on the characteristic of the biomass, how much lipids, because here we are dealing with substances that are sticked with non-polar solvents, because these are the substances that move from a polar, very polar environment, that is a water environment, to a non-polar environment, that is a lipid or a biomass or organic molecules environment. We may write that the concentration in the lipid fraction, the concentration in the biota is equal to the concentration in the lipid fraction of the biota multiplied by a coefficient F lipid that tells us, that is a percentage telling us how much of the biota biomass is lipid. So we may wonder if this is true for all substances, but as a first assumption, we may write that the concentration in the biota is liquid is equal to the concentration in the lipids multiplied by the concentration, by the percentage, the fraction lipids, so the percentage of the lipids in the biomass of the biota. If we put this together with the definition of the KOV, the octanol water partition coefficient, so we may write that the KOV is equal to the concentration in the lipids divided by concentration of water. Of course, with an octanol water partition coefficient, because in this case, the concentration in lipids plays as the role of the concentration in octanol, while the concentration in water is the water partition. If we put all these together, we obtain that the bioconcentration factor, BCF, is equal to the lipid fraction of the biomass times the KOV. So you see that in this case, we are describing the movement of the substances between the biosphere and the hydrosphere as dependent on the lipid content of organic matter, so fractional lipid, time characteristic of a substance in terms of the octanol water partition coefficient. In general, we may generalize the model by again going to log-log representation. So we may write that the log of BCF is equal to the log of the fractional lipid plus a coefficient times the log of KOA. So we shall observe that the bioaccumulation factor that has to do with uptake of toxic substances from the water column by plants and animals. So the bioaccumulation factor, that is the ratio between the concentration in the biota and the concentration in water, concentration in bio divided concentration in water, is modeled by this kind of modeling approach. This model, that is called the bioconcentration factor model, as we have seen, it is simplified, or if you want, it is generalized by putting the dependence, by including the dependence of the concentration of the bioconcentration factor on not directly on KOA, not linearly on KOA, but more generally by an exponential of the KOA, and the exponential is beta, be another factor, another parameter, that may become a calibration.
Yes, sir.
Model. Yes.
Yes, sir. In the general formula, what does that B represent?
In the general formula, you mean this one, the
Where
first
we
one?
have
Bioconcentration
logarithm. Where we
factor
have the logarithm
is equal to the concentration in the biota divided by the concentration in water. This B refers to the concentration in the biota, right? In the generalization of a model, so here, you simply include the fact that the model, as often happens in ecological system, is not linear. So there may be some effects like, for example, saturation effects, or like, for example, the fact that if there are too much of too high concentration of a substance in the water column, then the adsorption process cannot proceed indefinitely. So we change the shape of our model by including a dependency on the KOA, but is not linear. Instead, it depends on an exponential of the KOA. So KOA elevated to a B parameter. Does this answer to your question?
Yes, sir.
Okay. Now that we have treated the equilibrium between the hydrosphere and the biosphere, now we are ready to treat the equilibrium between lithosphere and biosphere. The equilibrium between lithosphere and biosphere, it is a mix-up of all the models that we have seen up to now. For example, again, we start by a bioconcentration factor models in which you write like the bioconcentration factor is equal to concentration in the biota divided this time by the concentration in the solid. Remember, this is the difference. Here we were looking concentration in the biota divided by concentration in water. Instead, now we are building our bioconcentration factor model by defining it as the ratio between the concentration in the biota and the concentration in the solid. But at this point, we need to estimate the concentration into the solid And how do we do that? By simply implementing to our model what we have just studied, so the transfer between hydrosphere and biosphere, and the transfer between between hydrosphere and biosphere, and the transfer between biosphere and lithosphere. How do we do that? We include the model we have just introduced, so bioconcentration factor in water divided by, again, this is an equilibrium constant KD, is equal to a lipid fraction of the organic matter, so of the body of the organism we are looking at, times the KOV elevated for generalization to a B constant, to B power, divided by another calibration parameter X times the fraction of organic carbon multiplied by the KOV, this time elevated to a different power. So if you end up by putting all this together, that in the case of a lithosphere-biosphere interaction, the bioconcentration factor is essentially equal to a ratio between the lipid fraction of the biota and the organic carbon content of the biota itself, so of the adsorbent. This is multiplied by KOV elevated to 0.09. So this is a very weak dependence on the KOV. So in the case of transfer from the lithosphere to the biosphere, we have a very weak dependence on the characteristic of a toxic substance in terms of KOV, meaning that different toxic substances in terms of KOV, so toxic substances with the different octane water partition coefficient, in general move the same way from the lithosphere to the biosphere, depending only essentially on the lipid fraction of the biota and the fraction on the organic content of the organic carbon content of the biota itself. Okay? This is a very, very short resume of all the ecotoxicology or ecotoxicological models that you should have already seen here and there during your career. And this is essentially what you need in order to describe the movement of toxic substances from the water column to the lithosphere, so the suspended particles, and from the water column and the suspended particles to the biosphere. Please note that organic matter or living organisms can absorb water with dissolved toxic substances, as well as solids with adsorbed toxic substances. So when we deal with the interaction between biosphere and lithosphere, we shall include also the interaction between hydrosphere and biosphere, and the interaction between lithosphere and biosphere. Okay, I think you have already seen all these models, so I'm not wasting too much time into going to the details of these models, because apart from the fact that they are mathematically very simple models, I assume that you have already seen several examples of that. Now let's go on to introduce some new models that will be helpful in describing physical processes like balance and transport and chemical reaction models. First of all, when we have to introduce physical models describing the transport of substances between the various geospheres, as the ecological modeler today knows very well, the first starting point is the choice of spatial and temporal scales. In particular, we may start by space, zero-dimensional. This is the case for lakes, ponds, and so on. Or you may use this zero-dimensional modeling also for describing more complex situations. So you may employ zero-dimensional series of models. For example, this way you may describe a river by assuming a set of points, zero-dimensional points, in which you define concentration, temperature, characteristic of a water column, and so on. And this way is the first approximation to monodimensional rivers, in which you may imagine to subdivide the space into more dimensions. Typically, if you have to describe systems like lakes, lagoons, or coastal areas, you will at least implement b-dimensional models, because verticality plays a relevant role in these cases, because stratification, as you know, in surface water bodies is a striking characteristic. But if you want to be very detailed, then you have to switch to three-dimensional models. And this is the case if you have to describe estuaries, sea, bays, coastal zones, and so on. When we describe three-dimensionally, our system, as you can imagine, will complicate our lives very much. What about time? Time depends on the process on focus. Example, networks are often static picture of exchanges of resources in system. So you may question yourself if networks that are static pictures are appropriate or a valid approximation for the processes you want to include into your system. In general, we have a graph, and we may conceive a graph of this type in which we subdivide the various processes in the three categories: physical, chemical, biological, and ecological. Four categories: physical, chemical, biological, and ecological processes. All these categories have different special scales. In particular, physical processes pertains to very small scales, while ecological processes pertains to very large scales. But a reverse consideration may be made concerning timing. Physical processes are acting on the scale of seconds, while ecological processes are acting on the scale of centuries. So you see, depending on which are the processes you are focusing on, this graph may give you a first guidance in selecting the appropriate spatial and time scale for your description. When you do this kind of analysis, you should be aware of the fact that there are feedbacks mechanisms from the various levels, so that, for example, from the ecological model description, you may have a top-down control on the lower hierarchical models, like the biological, chemical, physical model. But it may happen also that you may have top-down control. So you may have the fact that physical models may influence the higher hierarchical levels of chemical, biological, or ecological model. Which is the proper scale? The question is maybe recasted in where is causality working. So we may choose the appropriate scale by asking ourselves who is doing what to whom. So who is changing and what it is changing. So it is just, as I already anticipated, it is a cyclic process, but you generally apply during the conceptualization phase of a model building, in which you define the scales and in which you define the complexity of a model by, for example, taking into account the possibility of various feedbacks at various levels. But please note that feedbacks inevitably bring with them non-linearities. So if you have feedbacks, you may expect that you may have a dependence to a square of some state quantity, state variables, and so on. So now I give you a very quick overview of the type of processes, and we will go in more detail on that tomorrow. Type of processes we shall describe are physical processes, but I mean transport or phase change. Transport means real movement of material. Phase change is changing from, for example, from solid to liquid, like ice melting, or from organic to inorganic, like chemical processes. In general, physical processes are well described by transport models, while chemical processes are well described by reaction equilibria, while biological processes, like for example, primary production, nitrogen cycling, biodiesel removal, and so on, are much more complicated, and they will include all the previous processes, physical and chemical, at various levels of detail. How do we start by dealing with physical processes? First of all, we shall introduction description of the mass balance. Remember, we start always from the energy conservation principle that is formalized into a continuity equation. If we focus on an elementary volume of my system, might be a portion of a lake, a portion of a savanna, or a portion of a canopy of a tree or whatever, we may identify infinitesimal elements by building cubes delta y, delta x, delta z, and we may describe what's happening into these cubes by describing what is going in and what is going out. So we may have an accumulation of something by simply making a difference between what is going in and what is going out. We may add some complication because we know that in a world of ecological processes, also chemical or biochemical reactions take a relevant role. So we may write that the accumulation in the elementary volume of a substance is equal to what goes in through the inflow minus what goes out through the outflow, plus minus reaction of changing of status or conditions or chemicals and so on. The reaction terms, beside the input-output are physical transport phenomena, the reaction term here shall include all the physical, chemical, and biological reaction. Physical, typically changement of phase, for example, solid water becoming liquid, or chemical reactions, for example, enzymatic reaction, or oxidation, or mineralization with our chemical reaction, and in particular, biological reaction, like for example, primary production, that is an increase in biomass of primary producers, that is plants and phytoplankton, or for example, the oxygen cycle, that is typically influenced by the presence of living organisms, because living organisms have the non-common property of being able to breathe, so they can change the equilibrium of oxygen. And in terms of mass balance, we have three general descriptions or three general models that the environmental engineer typically applies. The first one is the CSTR, by far the most applied in all situations. CSTR stands for continuous stirred tank reactor, so it is a totally well mixed reactor. So you describe your system as a zero-dimensional system in which turbulent diffusion dominates, or in other condition, you may have a PFR, plug flow condition. So these plug flow reactors are situation in which you have advection but dominates. Typically, this is for rivers. So these are monodimensional models. Or you may have mixed flow reactors, MFR, that are controlled by dispersion and advection. This is typical for estuaries, coastal zones, and so on. How do we implement a CSTR model? We start, for example, from a CSTR, but is a totally well-mixed container. We have a load function. It is a concentration that is entering into the container transported by a discharge Q. Q is cubic meters of inflow water times the concentration of the substance in water, and then you have an output concentration C. Again, we write our continuity equation or conservation of energy, if you prefer energy slash matter, but it's the same, because as we have seen up to now, we easily switch between matter, between matter to energy. So we switch between milligrams to joules quite easily because we have conversion factors that tells us how much energy is contained in the per unit volume of different types of biomass. So we may write what the accumulations of the volume of the system time variation in time of concentration of your substance is equal to the load function, that is a function of T time, minus outflow, minus settling, minus the term related to chemical reactions of the transformation of substances. So accumulation is equal to input minus output minus reaction. Always the same story. If we substitute this the load function into this equation, we end up with a differential equation, first order differential equation, in which we describe a variation in time of concentration of a substance as a function of the loading function times minus the discharge times the concentration in the outflow, this is concentration in the outflow, minus the concentration that is taken away by settling, and AS is the settling area, V is the settling speed, minus the change in concentration due to chemical or biochemical transformation. Again, you know very well how to solve this differential equation, which is the only function whose derivative is equal to a function itself. The good students answer the only function is the exponential function. So that we end up with by saying that the concentration in the outflow is equal to the concentration in the inflow. So the initial concentration multiplied by a negative decreasing exponential, in which the decreasing coefficient lambda includes all these terms related to the settling and to the outflow and to the chemical transformation. So lambda includes the chemical partition coefficient, includes the settling speed, the settling surface, and the inflow or the discharge of the system. Then you need a particular solution that depends on the loading function. Let's see some examples. Let's consider a loading function in the form of a pulse. This is your neighbor that is going to the nearby the nearby ditches, and discharges as a tank of some toxic substance instantaneously or of a sudden into your river. Then the loading function in this case is m, so the quantity of material discharged all of a sudden at time t0, then the concentration obtained from the CSTR modeling approach is this one. And if we use this value of a parameter, the concentration in time into your river has this kind of shapes. Of course, with different curves, moves according to the changing values. M is the quantity of material discharged all of a sudden. This is a Dirac function. This means that this quantity is 1 at t equal to t0 and is 0 elsewhere. So M is the total quantity of discharged materials, V is the volume of the system, A is the settling surface, so if you want the bottom area of the system, Q is the discharge, so how much water is flowing in cubic meters per day in the system, Vs is the settling velocity, and K is the chemical transformation coefficient.
Dunque devo cominciare anch'io adesso, posso?
Sì, dammi ancora 3 minuti. 3 minuti.
Sir, please, the equation is not clear.
Sorry?
The equation is not clear. What does L stand for? The equation L equals to M.
L or M? M is mass.
L.
L is the load function. The load function, so how much material is arriving to the system at time t, is equal to the totality of the material that is discharged. This is the case of a pulse function at the time t0. So L is a load function, and the load function in this case is a pulse. Everything is discharged all together in one instant. So my neighbor is discharging his shield into the river, into the nearby river, or in one event. Is it clear?
Yes, sir.
We may see example of different loading functions, and we are quickly going toward the end of the lecture today because I have to go away now. And we can describe the effect of a different loading function, for example, a step function. The step function, we will have that the load will be 0 if time is smaller than 0, and the load will be constant L if time greater than 0. So we say that the polluting event is starting at time 0. Before this time, no pollution. After this time, constant pollution. And if we employ this loading function with our CSDR model, as we have derived it before, what we obtain is curve of these types. So you see that the concentration in time reaches a plafond, and after a certain point, the concentration doesn't change anymore. Why this? Because what's happening here? You have connected the discharges of your industry, or you have connected a tube of toxic substances, but is permanently discharged at a discharge queue as a quantity of toxic substances into your river, onto your water body. Then by this CSTR modeling, you discover that due to the fact that there is settling, but there is discharge, but there are chemical transformation, after a certain while, the concentration in the water body reaches a kind of plafond and remains constant all over the time. This is due to the fact that you have connected the tube onto your river, so you are discharging constantly in time a given quantity of material. Let's see another example. That is a pulse event of pollution. So this is, for example, I am connecting a tube, and after a while, I disconnect the tube. In this case, the loading function has an exponentially decreasing function. So this is typically what happens in a storm water runoff events in sewage system. When you have a first flash of storm water, you have a peak in load, and then after the time, as the time increases, you have a decrease in the concentrations due to the wonderful purification system that is called dilution, purification by dilution. So if you want to describe, for example, first flash events of pollution, you will obtain this kind of solution from the CSTR model approach. So you see again, you have
Buongiorno.
an increasing peak that is going to
Ciao a
decrease
tutte,
in
ben
time.
ritrovati, ben ritrovati.
Okay, for now we stop here
Buongiorno.
and we start tomorrow in the afternoon at 2 p.m. Yaoundé
Siamo in
time.
12,
We
sì,
continue
15
discussing
seduti oggi.
CSTR
Allora,
models.
questo è
Okay,
l'incontro
are you ready?
conclusivo.
Okay, sir.
Adesso vediamo.
So we will see
forse la parte
tomorrow.
più noiosa,
Now I stop, I
quello
stay in the
che
class
abbiamo
for
fatto,
5 minutes.
che
So
è
if you have
quella
to
della
pose any
valutazione del
question, please,
progetto.
I wait for
Vi
your
faccio
question,
vedere un
otherwise I
po',
close the class.
cioè,
Ok?
un po' la parte teorica, come valutare questi progetti, e poi vi faccio vedere un progetto in particolare, come è stato valutato.